are using Hubble to investigate some of the deepest mysteries of the universe.
One of the primary things Hubble has been doing is looking at the atmospheres around exoplanets.
If you had asked the guys who built Hubble and designed Hubble, they would have sworn Hubble could never, ever do this.
That's one of the things I love about Hubble, is that it ends up giving us new questions, new mysteries to explore.
My name is Larry Dunham. I'm the Chief Systems Engineer for Flight Systems here on the Hubble Space Telescope. I started on the Hubble program back in the summer of 1982 when Hubble was being built out in California. First telescope in space that'd be designed so that we've got what we call orbital replacement units. They're modular boxes with handrails on them so the astronauts can go up and just pick and play. They've got nice connectors on them that make it easy for the astronauts with their big gloves to be able to put them in and out.
We've had 5 servicing missions. We have replaced some equipment multiple times, especially the instruments. We're always going with the advanced technology.
The telescope we have today on orbit is not the telescope that we launched originally. We've been able to replace all 5 of our science instruments with instruments that have the technology that didn't even exist when Hubble was being built originally.
The Hubble Space Telescope is really an observatory because it has several science instruments, several modes of operation. We have multiple cameras, multiple spectrographs. They each have different capabilities in terms of their sensitivities or the kinds of frequencies they can receive of the electromagnetic spectrum. We can also use Hubble in different kinds of intriguing modes depending on what we're trying to observe.
There are different types of observing scenarios, and one of the things the scientists have been able to do is they've been able to come up with very interesting and unique observing scenarios that allowed them to do science that they never thought they could do before.
Because the Hubble Space Telescope has been operating for a long time, it's giving us what we need to explore the universe in deep ways that would never have been possible when Hubble was first launched. For example, scientists wondered whether we could use Hubble in an innovative mode in recent years, basically scanning objects slowly instead of just staring at them. In some cases, that gives us a higher sensitivity to what we're trying to observe. And we're using that special mode on Hubble now to get better information about many types of things in space, including to be able to study planets around other stars, what we call exoplanets, planets outside of our own solar system.
What Hubble's been able to do is as the planets go in front of the stars that they're going around, the spectrographs can detect changes, very small changes in the spectrum. This has allowed them to do exoplanet atmospheric studies. This is something that Hubble has sort of really stepped up to the plate and has been just phenomenally good at. Spectrographs have really sort of been leading that. If you ever see things about, oh, a new exoplanet was discovered that has this in the atmosphere or that in the atmosphere, or we think it's made of this, it's the spectrographs which have shown you that kind of information. For doing a lot of the exoplanet observations, you have to catch what's known as a transit. One, the orbit of the exoplanet has to be such that it's going to go between you and the star it's going around. We can't just do an exoplanet observation whenever we want or whenever it's convenient. We have to do an exoplanet observation when it's first starting to go into the star. And so they have to know very accurately the timing of that. We have to schedule it ahead of time. This is not something that Hubble can get around to when it wants to. We have to say, no, at this point in time, on this date, you have to be pointed here and you have to be looking here. We had to really think about how to schedule this. A lot of thought goes into it. A lot of thought goes into the planning and of the execution.
The Hubble operations team are quite willing and capable of using the telescope in new modes and new innovative ways that enable us to accomplish science that we wouldn't otherwise be able to accomplish. We asked them, would it be possible to use Hubble to track something moving quickly across the sky? And they figured out a way to use Hubble in a vast tracking mode that enable us to do explorations and discoveries that astronomers didn't envision using Hubble for when it was first designed.
Now, when we're observing our planets, when we're observing Jupiter or Saturn or Uranus or Neptune, they move also. We have to move the telescope because they're just going around the sun. They're actually moving because they're really moving. So we have to move with them. We're observing asteroids or comets. We have to chase after them.
Oumuamua, we know came from outside of our solar system, is like a big asteroid that was detected whizzing through our solar system. We wanted to use Hubble to observe this as well, and we were able to track it. This is not a simple operation. It's moving at more than 100,000 miles an hour, so being able to observe this and track it is a wonderful capability that the operations team has enabled Hubble to have.
The telescope is big, it's massive, it moves about the same speed as the minute hand on a clock. So to move from pointing one thing to go completely around the other one takes us a half an hour. It is not a very fast motion. We actually use a very interesting technique. It's using Newton's third law. We have these very large reaction wheels on it. They're about 2 feet across, very, very heavy, very, very massive wheels. You start spinning those wheels one way, the telescope will spin a little bit in the opposite direction. This is how we can move the telescope from one part of the sky to another part of the sky.
Once we've moved the reaction wheels and we've moved the telescope so we're in the right spot, now we have to get in the exact location to put the target in the science instrument aperture.
What's going to happen now is the FGSs are going to start talking to the telescope, talking to the flight software computer and saying, I want you to move the telescope over here a little bit to be able to position the science for the science aperture.
Most of the time we use the Hubble Space Telescope to do observations that have been planned quite a bit in advance. Observers around the world, astronomers will write proposals. We will then take those accepted proposals and observe whatever it is that the astronomer has proposed. But sometimes there are things that happen that are unexpected or rapid events that we need a more rapid response.
We have a capability of what we call a target of opportunity. And that's when something unexpected happens in the universe that astronomers, they want to immediately jump on that as fast as possible with Hubble. Case in point was the gravitational wave detection to neutron stars colliding. A target of opportunity was submitted for Hubble to actually go look at the remnant and see if we could find it.
We had the engineers run through it. We got new commanding sequences from the Space Telescope Science Institute. We were able to run all that through, and then we executed on orbit.
We have to respond very fast. We produce a new schedule and set of command loads.
We can modify a lot of the flight software, modify how the instruments are commanded. It allows us to change. We can react very quickly. What Hubble has done compared to what we were thinking Hubble could do is just amazing. Hubble's had its fingers in almost everything, a neutron star collision, looking for all the supernova, all this stuff going on with dark matter, dark energy, exoplanets. Hubble has just been constantly finding new things. Now we're looking at these interstellar comets and these interstellar asteroids visiting us. It's really been spectacular to watch.
There really are two key aspects to Hubble's design that have enabled us to last the 30 years that we have, and that is really the redundancy that we have on board, and then it's the servicing, putting in new and improved instruments, and being able to improve the hardware with lessons learned over the 30 years of Hubble operations. We are now at our peak performance.
The Hubble Space Telescope has had a profound impact, not only on astronomy. It showed that humans in space and science can go hand in hand to enable us to explore space in richer ways than we could ever do with either just astronauts alone or just with instrumentation alone. By using these skills together, new vistas of exploration are open to us, and that lesson is something we're still benefiting from as we envision future space exploration.
Go ahead. Okay, we have a go for release. Okay, Charlie.
It's amazing with a program that's lasted the duration that Hubble has lasted, that the astronomers up at the Space Telescope Science Institute continue to come up with new things that they want to try to do with Hubble, and we certainly hope that we'll be able to continue to provide that kind of capability to them into the late 2020s and beyond. What you're looking at with a telescope, of course, is the light from billions of light years away. So the further you look, the more you're going back towards the Big Bang and understanding how the universe was formed.
The Webb telescope will be groundbreaking because it has capabilities that are different than the Hubble Space Telescope.
We have equipment that is so much more powerful than anything we've ever had before that it's almost impossible to tell what we will discover.
Hubble's accomplishments include something called the deep fields, looking out into space and collecting light, sometimes for many days. These deep fields have revealed visually to us a universe absolutely teeming with galaxies, hundreds of billions of galaxies.
One of the neat things about the ultra deep field, and one of the things that made it so unique was how long it took us to take that image. There's an exposure time that's expressed, I think it's 11.2 days. It's a very, very long exposure time. But probably what's more important is how many orbits it took us to do that. 400 orbits of Hubble data to take that image. You only get 15 orbits a day. To take 400 orbits and say, we're going to observe this one spot in the sky for 400 orbits. And the really unique thing about that was they picked a spot where there wasn't anything. They looked and they said, there's absolutely nothing here. And they said, you want to spend 400 Hubble orbits looking at nothing? And they said, yes, because we want to see what it can see. And I think the results from the science, I mean, it was amazing. What they saw was spectacular.
Hubble had spent 2 weeks taking pictures of empty places in the sky, and they saw they weren't empty at all. They were thousands and thousands of galaxies.
We were amazed how many galaxies we've found, and we continue to go back to that portion of the sky to increase that visibility.
The Hubble Space Telescope is an outstanding time machine. It's incredibly important for our studies with the Hubble Space Telescope to realize that when we're looking at a galaxy, we're seeing it as it was millions of years ago, sometimes billions of years ago. It's taken that long for the light to get to us.
What you're looking at with a telescope, of course, is the light from billions of light years away. So the further you look, the more you're going back towards the Big Bang and understanding how the universe was formed.
What Hubble has revealed is that the universe has in fact changed over these billions of years of time. The early galaxies, the very distant ones as we see them, are simple. Sometimes they're messy looking, they're small, they haven't had time yet to form that grand spiral structure. Over time, we see galaxies actually merging with other galaxies and growing bigger and bigger, and those mergers can look like train wrecks in our Hubble images.
These very, very deep exposures that Hubble has been able to take, we have seen right to the edge of the universe, 13.5 billion years. When Hubble was first designed and envisioned, it was never thought it could actually see that far out. But because of the advances in the instruments that we've been able to put up on the telescope, and also the cleverness of the scientists, they've come up with very interesting observing scenarios, doing these really deep exposures where we just sit there for orbit after orbit after orbit, gathering the photons. We've been able to push Hubble out very, very far.
As Hubble looks out into these fields of galaxies, we sometimes see clusters of galaxies. These are galaxies that are held nearby each other by their mutual gravity. These clusters are massive conglomerations. There's so much mass that they have an actual observable impact on space-time itself. Einstein predicted that mass distorts space, but we didn't realize we could actually see the effects of that. But with Hubble, we have been able to see distortions in space around clusters of galaxies. The way we see that is when light from a background galaxy travels through that cluster of galaxies or around it due to this gravitational lensing effect. The lensing also magnifies that background galaxy, so if we look in some of these distorted arcs, we can see more detail than we would ever have been able to see without gravitational lensing, nature's boost.
There are observations where we're explicitly looking for the lensing, and they're getting science out of that just otherwise would just not be doable. Hubble has really taken that to a next level. It's doing large amounts of astrophysics that it's just never been able to do before.
Some of what we're doing with Hubble is to prepare for the new James Webb Telescope, which we anticipate launching in 2021, which will be able to see farther into the infrared part of the electromagnetic spectrum. That enables us to see some galaxies that are difficult for Hubble to see because they're so far away that their light is traveling through us through expanding space and gets stretched out into redder wavelengths, often far into the infrared part of the spectrum, even sometimes beyond what Hubble is able to detect well. The Webb telescope will give us more information about some of those very distant galaxies.
The James Webb Space Telescope is the follow-on telescope after the Great Hubble Telescope. It extends the discoveries of Hubble into the infrared spectrum region. We think that the first objects that grew out of the Big Bang material probably happened in about 100 million years after that start. And we think the Webb telescope can pick them up. They're rare, they're hard to find, but they should be there. The farthest we've been able to see with the Hubble telescope goes back about 800 million years after the expansion began. So we think we get much closer to the first objects with the Webb telescope.
Hubble gives information that the Webb telescope cannot give about visible and ultraviolet emission from things in the universe. And when we have all that information coming in at the same time, it's like a banquet of scientific return.
Now when we get the complete picture of every wavelength you can possibly see from ultraviolet to infrared, we hope to have the story of the growth of the first galaxies from the primordial material. So that will be a huge accomplishment that depends on both pieces of equipment, the Hubble telescope and the James Webb telescope working together.
So astronomers are very excited about this probability that we'll have both the Hubble Space Telescope and the Webb telescope operating at the same time for quite a few years. That will give us an abundance of new understanding about the universe. And already right now with Hubble, we're doing preparatory observations for the Webb telescope. We're using Hubble to do things, for example, like surveying distant galaxies to find out which ones would be prime targets for the Webb telescope. In fact, scientists around the world are proposing observations with Hubble right now specifically to help us learn information that will be useful for making the best use of the Webb telescope as soon as it's launched and gets going in its science observations.
I think the Hubble telescope has been the most productive science instrument ever built. In astronomy, there's what we knew before Hubble, and now there's what we know after Hubble. They're so different. Of course, Hubble has now had a life of 30 years, so it's had a long time to make this revolution happen. So it's not all at once. It's a gradual revolution, but it's still a huge revolution. Technology has changed dramatically over the 30 years of life of the Hubble telescope. So you couldn't even have imagined when the Hubble was launched that we would have the wonderful cameras and spectrometers that we buy today. We figured out how to send astronauts, we trained the astronauts, we figured out what instruments could be put in, we figured out how to repair everything that went wrong on the Hubble, and it's still alive. It's today, 30 years after launch. And I am so thrilled to say that our people were able to do that. That's the operations team that makes this possible. It's a miracle as far as I'm concerned, because it didn't have to be that way, but they made it happen.
Sub-Neptune quickly lost its early hydrogen and helium atmosphere due to the intense radiation of the young hot star it orbits. Then, the planet was stripped down to a bare core about the size of Earth, and that's when things got interesting. To the surprise of astronomers, Hubble observed an atmosphere which, according to their theory, is a secondary atmosphere that is present now. Based on a combination of direct observational evidence and inference through computer modeling, the team reports that the atmosphere consists of molecular hydrogen, hydrogen cyanide, and methane, and also contains an aerosol haze. Scientists think hydrogen from the original atmosphere was absorbed into the planet's molten magma mantle, then slowly released through volcanic processes to form a new atmosphere. Though this hydrogen continues to escape into space, the secondary atmosphere is replenished by volcanic gases that seep through cracks in the planet's thin crust. Scientists are wondering how many other planets might have started out as gas giants but became smaller and rocky after their early atmospheres evaporated away. Astronomers hope to use the upcoming James Webb Space Telescope's infrared vision to detect hot areas of volcanic activity on the planet. GJ 1132b might be orbiting a distant star 41 light-years away, but thanks to the Hubble Space Telescope, it just got a little bit closer.
Just to be 100% sure. The moons in our solar system are very diverse, some with liquid water, some that are potentially habitable, so being able to observe moons in different solar systems would give us a whole new treasure trove of interesting worlds to study. The team of astronomers from Columbia University sifted through data from 284 Kepler measurements of transiting exoplanets. A transit happens when a planet passes directly between us and its star and blocks out a small portion of the star's light, which produces a dip in the amount of light coming from that star over time, called a light curve. If there's a moon on either side of the planet, we might be able to see a second, smaller dip in the light curve. Making transit measurements and processing the data into a light curve can be very tricky though, so scientists need to observe multiple transits in order to get convincing evidence of an exoplanet or an exomoon. Out of the 284 planets the team looked at, they found one planet with an extra wobble in its light curve that might be a moon. This planet, Kepler 1625b, orbits its star once every 9.5 months, so it takes years to observe multiple transits. The team only had Kepler data from 3 transits of this exoplanet, so they sent a proposal to the Hubble Space Telescope to capture more data of this possible exomoon. Hubble can measure light curves much more precisely than Kepler, so Hubble can more definitively confirm or disprove the existence of this exomoon once it gets multiple transits. So far, the team of astronomers has collected Hubble observations of one transit of exoplanet Kepler 1625b. Hubble measured the light coming from the star over a period of 40 hours. About 7 hours into the observation, the planet started its transit, which was about an hour earlier than predicted. A tantalizing piece of evidence that the planet has a large moon, because a moon would cause the planet to wobble in its orbit. The planet transited across the face of its star for 19 hours, as expected. Then, about 3.5 hours later, a second, smaller dip in the light curve started. That right there is intriguing evidence of an exomoon. The Hubble observation unfortunately concluded before the possible moon finished its transit, so Hubble hasn't yet observed a full transit. This light curve appears like it shows an exomoon, but we can't say it's a definitive detection until Hubble observes at least one more transit. If this is actually a moon, what do we know about it? The planet Kepler 1625b is likely several times the mass of Jupiter. Its possible moon appears to be about the mass and radius of Neptune. The ratio between the mass of this planet and its moon is about the same as between the Earth and our moon, but scaled way up. Neptune-sized moons are obviously not something that exists in our own solar system, and we're not sure exactly how such a moon would form. When scientists first started discovering exoplanets, a lot of them were several times the mass of Jupiter because big planets are easier to detect. So a similar thing may happen when discovering the first exomoons. Finding planets and moons so different from the ones in our own solar system gives us a lot more knowledge of the many diverse ways planetary systems can exist. In the near future, scientists hope to use the Hubble Space Telescope to try to confirm the discovery of this exomoon, and then they'll use Hubble for follow-up observations of other planetary systems discovered by observatories like Kepler and the recently launched Transiting Exoplanet Survey Satellite, TESS. And then the upcoming James Webb Space Telescope will be able to take high-precision measurements in infrared wavelengths, which combined with Hubble will allow for detailed characterizations of a whole bunch of really interesting exoplanets and likely exomoons. So, if you like planets, and honestly, who doesn't? Stay tuned to learn about all sorts of fascinating new worlds.
The Hubble telescope is composed of several different instruments, and outside of those is something called the primary mirror, where all the light bounces off of and goes into the instruments. That's where the flaw was. So the problem was something called a spherical aberration. What exactly does that mean?
It means the primary mirror had the wrong shape. That is, it's a shallow bowl, effectively, that brings light to a focus. It's a little too shallow. It rendered the telescope fundamentally unfocusable.
So it was a little bit out of tolerance on that primary mirror, and it was affecting all the instruments in the Hubble?
All 5 scientific instruments on the Hubble depend on a sharp image. That's the whole point.
So Hubble's sitting in the doctor's chair, and it has the eye chart in front of it, and instead of seeing the letter E, it sees the letter F.
Worse, what it sees looks like a squashed spider.
But it's way up in space, and you can't get it back here, so how do you fix it?
Well, if you're born with eyeballs that don't quite work, you don't go and buy new eyeballs, you buy a pair of glasses, and that's the approach that we took.
The wide field and planetary camera known as WIFPIC relied on light from the primary mirror.
The light from that primary mirror all comes down to a focus inside our camera on a mirror that looks just like this. And this is now an opportunity for us to correct the curvature, the shape of the primary mirror right here. We simply put the same error in, reversed, and corrected. The Hubble telescope was designed from the outset to be serviced every 3 years by astronauts.
The entrance, you can take it away.
The camera is designed to be replaced in space. That's the one thing that was really just waiting for us to take advantage of.
Looks like it's in there. Yeah, mine's beautiful. Okay.
So what was the outcome?
At the Space Telescope Science Institute, way down in the basement, there were a bunch of us watching. And the first image, which was of a star, looked good. So we knew right away that we had a fix. And everything that Hubble was supposed to do was now going to happen.
So I think I speak for everyone when I just say thanks to you and your team for all the hard work you put in fixing Hubble, because now we have these images really forever that we can appreciate. WIFPIC 2 went on to become the workhorse for the Hubble telescope, and it lasted for more than 15 years. Well, now you guys can check it out at the National Air and Space Museum in Washington, D.C., and we'll see all of you on another episode of Crazy Engineering.